Hello, today I will be talking about molecular shapes, bond angles, and polarity using trinitrotoluene, also known as TNT, as an example. This right here is the trinitrotoluene molecule, complete with electrons in a complete Lewis structure. First, let's talk about molecular polarity. As we can see, this molecule is very triangular, with 3 of the same clusters of NO2 on 3 corners of it, with a methyl group on top, which is 3 hydrogens bonded to a carbon, and 2 hydrogens bonded to carbons in the benzene ring, right in the middle. Let's first draw a few polarities, just to get a rough sense of what the overall molecular polarity of this molecule might be. So as we can see, we have a middle ring of carbons. These are much less electronegative than any of the nitrogens or oxygens that we have on these 3 corners. So we can draw arrows from these clusters towards the carbons. And I'll draw them in red. So as we can see, the overall polarity facing towards these 3 nitrogens. However, since carbon is much more electronegative than the hydrogen, the bond polarities for the hydrogens in carbon bonds will be like this. The positive end facing towards the hydrogen, since carbon is slightly more electronegative than hydrogen. My prediction for the overall bond polarity of this molecule will be facing this way, due to the fact that these 2 vectors on these 2 corner NO2 clusters next to this methyl group, the top, with the carbon surrounded by 3 hydrogen molecules, will cancel out these 2. We now go to a 3-dimensional view of the molecule trinitrotoluene, and we can see here that is a very flat molecule. We can see here that there are 3 clusters of NO2. And these 2 are right next to the methyl group up here, the carbon bonded to 3 hydrogens, which is also bonded to this carbon, which forms this benzene ring. This benzene ring also is bonded to these 3 NO2 groups, and these 2 hydrogens down here. So, if you look at the MEP surface, we can see that the more negative areas, shown in red, are pointing towards each of the oxygens, where the more positive areas, shown in blue, is a cloud surrounding this middle benzene ring. This hexagonal ring, 6 carbons, which are single bonded and double bonded to each other, forming a central structure of which everything else is bonded to. As we can see, this carbon bonded to these 3 hydrogens is much less negative than these oxygens down here. We can then extrapolate that the bond polarity, overall bond polarity, will be facing this way. So let's clear this at the overall molecular polarity. And as we can see, the vector is pointing towards this bottom cluster of NO2, nitrogen dioxide. Therefore, this confirms our idea that these 2 cancel out, and that since this is less electronegative than this cluster here, the overall molecular polarity points towards this NO2 cluster. Now I will talk about bond angles and how they correlate to the number of bond domains, so that you guys can predict the bond angle when you know the quantity of bond domains. For example, if you have 2 bond domains, then you know for a fact the bond angle will be 180 degrees. This is due to the fact that bonds want to be as far away from each other as possible. So you can't get farther away than on opposite sides of something. With 3 bond domains, each atom will still repel each other just as much, but since there's more of them, there's less space for them to repel each other, less space for them to have. So the bond angle will be smaller than 180 degrees. In fact, it'll be 120 degrees. With 4 bond domains, the atoms have even less space than before. So the bond angle between each of them will be 109.5 degrees. However, these three examples do not take into account double bonds and lone pairs, which would affect the bond angles of each individual bond. Coming back to the trinitrotoluene, the three structures we will be discussing is this structure at the top, a group of hydrogen carbons, this group here, these four carbons, and this middle ring right here, this benzene ring. Let's start with this group of hydrogens and carbons at the top. So we can see there are 1, 2, 3, 4 atoms bonded to this central carbon molecule. Since there are 4 atoms bonded to this central carbon, we could determine that the molecular shape would be tetrahedral. The electron domain geometry would also be tetrahedral, and the bond angle would be 109.5 degrees. Now let's talk about this 4-carbon structure. Since there are only 3 bond domains, this structure will be trigonal planar. The structure will be flat, arranged in a triangle, since there are only 3 bond domains. However, the bond angles will be slightly different. These 2 bond angles will be slightly greater than 120, while this bond angle will be slightly less than 120. This is due to the fact that this double bond pushes on these 2 carbon single bonds more so, therefore pushing them closer together, making that angle less. The last structure I'm going to talk about is this middle group of carbons, known as a benzene ring. When 6 carbon atoms align themselves in a hexagon, they form a benzene ring, with every other bond being a double bond and every other bond being a single bond. Here we see 2 benzene rings, separated by this red dotted line. As we can see, they are resonance forms of each other. As you can see, the positions of the single bonds and double bonds are flipped in either resonance structure. This is to make sure that whenever something is bonded to it, there are always 4 bonds to the carbon. Since carbon doesn't like to have lone pairs, it prefers to have bonds. Every other one will be a single, and every other one will be a double bond. Here we can see the actual molecular structure of benzene, from which the benzene ring gets its name, C6H6. As you can see, every carbon has 4 bonds, and every hydrogen has 1 bond each. Therefore, all the octet rules are completed. We can see on the far left that the benzene ring here shows 3 double bonds and 3 single bonds, while the structure in the middle shows a hexagon and inside a circle. Is a fairly good representation of the fact that the bond order of each carbon-to-carbon bond is 1.5. Now that we've talked about trinitrotoluene's molecular shapes, bond angles, and polarity, now it's time to talk about trinitrotoluene's, or TNT's, properties and uses in everyday life. Trinitrotoluene is lucid and explosive. Insensitive to friction and shock, it's very stable and it has a reduced risk of accidental detonation. It's non-soluble in water. As an explosive, it's used in hydraulic fracturing or fracking to recover oil from shale formations. It's also used in mining as a general explosive. One of its special particular uses is used in calculating explosive power as a scale. A megaton, which is equivalent to 1 million tons of TNT being detonated, is used as a scale to determine explosive power of nuclear weapons. Thank you so much for listening.